Thank you for that introduction. I guess I don't really introduce myself, so I won't. Let's just take a look at what we're actually doing here. Why are we here? I'll talk about some motivations for mostly this talk, but also kind of partially the project that this talk was inspired by. We'll talk about some queries that we want to do over some sets of data. We'll talk about the low-level bits and bytes of the format. So if that's not your thing, then this may not be the talk for you. But if you want to hear about all the way data is arranged, then this should be exciting. And then we'll look at some micro benchmarks that don't have anything to do with reality and some future possibilities for this project. So motivations. As always, we can look to Hacker News for inspirational quotes. So the field is too in love with horribly inefficient frameworks. Writing network code and protocols is now considered too low level for people. When I submitted this talk, I did not have a quote that really fit the ethos, but this is definitely it. I think people are too afraid to look under the covers and too scared of maybe making up their own format, or at least taking a look at what happens underneath. So when you get down to it, computers make meaning out of voltages. The way people use computers, we assign meaning to all of these different voltages. You have billions of transistors in your Intel CPU, and they don't mean anything unless we assign a meaning. And serialization itself is everywhere, and everything you do, because everything comes down to voltages. So you have network protocols, you have layer 2, layer 3, even the physical layer has its own way of serializing data. Video encoding, which we do quite a lot of. Machine code, if you imagine maybe the Intel microcode has its own format inside. That's proprietary, so we don't know. HTTP2 now has non-ASCII headers, so there's a serialization format there. Hard drive communication, serial ATA. Video display. I actually had a project in college where we took this tiny little CPLD, which is sort of like an FPGA Lite, and we had to drive a VGA display with it. And that was very eye-opening because we had to know how to generate a clock and to put the RG and B signals on the wire at the right time in the right place so that we could actually display a picture. And that was just very instructive. And in my opinion, engineers should know what's inside the black box. You should be curious to know what's going on underneath, and you should investigate just to see how it works. So that's the motivation for giving this talk. Now, we'll talk about some generalities about the project. It's not a public project yet, so I can't really give too much detail. So I'm going to posit that JSON is the de facto serialization format between services. And this may be controversial with some people who are using only gRPC and protobuf, but in my experience, this is the format that people use. So there's a common pattern when you're getting a document from a service somewhere else, or maybe from a cache or what have you, where you'll get the entire thing. You inflate the serialized data maybe into a POJO or a Go struct or what have you, and then you'll walk the data structure and you'll get the pieces that you actually wanted out of that document. The new pattern, and this isn't groundbreaking, there's other sort of systems that have done this before, is to query the document, get just the data that you need, and you still need to inflate it into something, but generally, the pattern ends up being such that it's beneficial to get just the data that you need to do this, and it ends up being more efficient. So what we want is to provide query capabilities over JSON documents, and we want those JSON documents stored as a byte array, but in such a way that it supports these queries that we were going to do. And just so everybody understands the JSON document that I'm talking about in this talk specifically, there's 7 types. A null is just a null. There's Boolean, true or false. Integers, which is new here because JSON, I think, technically doesn't have integers. It's a full 64-bit integer. Floating point, full 64-bit floating point. If my memory serves, JSON doesn't specify the length, so some JavaScript implementations have a 50-some-odd bit floating point value, which is really weird. Regular strings, as you would expect, and then there's 2 composite types. Those were the scalars. This is the composite types, where you have an array and you have a map. So the array can store any one of these 7 types in it, and maps are a string to any one of these 7 types. So it can be any type in there. It's not strongly typed. Okay, let's move into what kinds of queries we want to be able to do on these JSON documents. So these focus more on the composite types. Mainly because those are far more interesting. That's not to say you can't do stuff on scalars, but this is just the core of the talk. So for arrays, we can index into an array. We can slice them. and we can iterate over them and apply a subquery to all of the elements. And for maps, you can access one or two or more keys and apply, well, you can grab the data out of there, or you can get just the keys out of the map. And the third thing is to iterate over the map key-value pairs and apply a query to the values and reassociate that with the key. So we'll dive right in. Array index, this should be pretty similar, or not similar, but should be pretty familiar to most of you. This query syntax is just made up for this talk. Don't worry too much about syntax. In this case, it just means grab the second element out of the array. So array 1, 2, 3, 4, 5. Your result's just going to be 3 because it's the second element in the array. Slicing. So this is more akin to Python slicing than Go slicing because we have negative indices also. So in this case, it's 2 to -1, which is index 4, and exclusive, just like Go. So in this case, we just get an array, subarray like 3 and 4. So for iterating over an array, we're going to apply our subquery here, which is just getting the 0th element out of the array. So you have this complex thing down here at the bottom that has elements that are the arrays themselves, and they have one element. So what we're doing here is just kind of unpacking these out of those subarrays, and we'll just get the arrays, or get the array 1, 2, 3, 4, 5. After applying that subquery to each one of those elements, we pack it back into an array, and that's your return value. Map access, so single key. Again, don't worry about the syntax too much here. Just say we're going to go get the value out of associated with key foo. We'll just get 3 back. So we have our map down here at the bottom, foo to 3 and bar to 4. We'll just get 3 because that's the value associated with that key. So for multiples, what we're doing here is effectively doing a projection of the map into a smaller space. So we're just taking just the keys that we want and the values associated with them. So in this case, we're just grabbing the values foo and the keys foo and bar and their associated values and putting them into our map to return. Keys is fairly straightforward, like you would expect it to be. You get an array back with strings. So it's just the string keys out of the map. This could be useful for like autocomplete or other things like that. Iterating over them is much the same way as an array, except now you have a key-value pair, and we're just applying this to the value. So in this case, we have arrays that are just single-element arrays, and we're going to get the numbers out of them, just kind of unpack those. So our result ends up being foo to 3 and bar to 4. OK. We'll go through a couple of examples here just to kind of illustrate it a little bit further. This is more complex of a structure. So we have foo and bar are keys, and they have very similar maps as their values. And this query is going to go over each one of these pairs and then go into the map, get the value associated with key 1, and then get the first element out of that array. And that allows us to sort of dig into this structure here and pull out just the numbers that we want. And this is recursive, so if you have maps of maps of maps, you can dive into those. So in this case, we'll get the map back foo to 3 and bar to 5 because we dug into that map and gotten the first element out of that array. And one more, grabbing the keys out. So the values here are just these maps of the string representation of a number to the number, 1, 2, and 3, 4, 5, and 6. So if we want to just get the keys out, we'll get back a map that has foo to 1, 2, and 3, and bar to 4, 5, and 6. And we'll still have, so we have that information now, and we can do what we want with it. So I know it was a little bit fast, but we have a lot to go through on the actual like bits and bytes pieces of this that help support all these queries. Again, we're dealing with what I call augmented JSON because we have integers now. There's 5 scalar types, null, boolean, integer, float, and string, and then we have 2 composite types, which are far more interesting than scalars, arrays, and maps. So our general format is going to look like this. We have 1 byte, which is the type. In this case, it would be an int. And then the data after that is entirely dependent on the type. And this 1 byte is going to be kind of our foothold into the record. This is more of like the how do you design a format. So you always have something in the beginning, something there that you can count on being there, that you know how to interpret, and you can use that to figure out what data you are going to look at afterwards. So we'll take a look at the scalars first. For a null type, there's just like 1 byte. There's nothing else associated with a null, so you don't need anything but the type. For a Boolean, there's a Boolean type, and then there's just a 1 byte, like 1 or 0. So it's just a 2-byte record. In theory, I mean, I could have packed like the 1 bit that we're using into the Boolean type, but that just complicates everything. It's more of a special case and sort of a design decision not to do that. Integers here, we have a type byte like everything else, and then we have 8 bytes of integer data, 64-bit integer, stored in little endian format. So this will be a little bit clearer with an example what little endian is if you don't know. The least significant bits come first. So in this case, if we're storing 4, we're going to have 04 as our first byte. So, and then it works its way to the left as you're laying out data to the right. And I mean, Go does this kind of for you, where there's a binary.littlendian.put int64. I think it's int64. It might be a uint only, but that does this for you. But just to see how the bytes are laid out, this is what it looks like. So for floats, it's much the same way. 64-bit floats, we have our type. And we have 8 bytes of data, that's the float 64. There's no binary little endian float, so you have to kind of reinterpret it as an int, and then you use the same way as you would store an int. So let's just take a look at an example. If you want to store 4.5, it's hex 4012. So, and then 12 zeros after that. So in little endian form, you have a bunch of zeros, and then 12 and 40 as your bytes. I think encoding Gob does this thing where it like flips the bits around. It does varint and other things so that it can compress it. But there's actually a good reason for leaving these as full 8 bytes, both integers and floats, which I'll get to kind of at the end of the talk. So for strings, this is the first time we've seen something that is variable in length, right? So what we have is our type, and then we have a length here that is always going to be there. We know we have this. This is our foothold into the rest of the data. So I just want to jump right into the example because it's a lot more clear this way, at least in my head. So if you want to store a string hello go, you have this 4 bytes of length right at the beginning. And we can count on those being there, even if it's 0. We know that those are going to be there so that we can interpret whatever comes after it. So in this case, we know we have to read 10 bytes of data. We can go read those, and in Go, you just cast back to a string from a byte slice, and it becomes a string again. For writing these out, it's literally the opposite. We just grab the byte slice of the string, grab the length, write that out, and then write out the string data. Okay, the composite types. These are a lot more interesting. So we'll start with the array. And remember, these actually have to store any one of these types of records in it. So this is a fully recursive data format. So if we have our type as usual, we have now like a header that exists there, and then all the data. And this data is just going to be all those records that we could put in the array, and they're just going to be packed together into one long like byte array, so that we have them all there. So what does the header look like? There's a varint here at the beginning. That means you'll have at least 1 byte. That is the number of offsets. And these offsets are actually like fence posts, which I'll try to illustrate more in a second. But they're fence posts around the data. So you have like a start and an end to every single record as you go down. And we have this interesting field called offlen, which is our length of the offset into the array. Now, why would we do that? So if you want to store a full like 64-bit integer, it takes a lot of space. It takes 8 bytes. But I'm not going to be storing 9 like septillion. I don't know what the maximum int64 is. Some huge number. We don't really need all 8 bytes. So what we do is figure out like the maximum length that you need in bytes to store the maximum offset. And then you can take that and pack integers as like 1, 2, or 3, or 4, or 5 byte like integers into like one long array, and you can calculate where those are. So to get them back out, you can extract them too. I'll show you an example, hopefully make that more clear. But once you get past like 5 bytes, you're in the exabytes of data, and we're just gonna have, We're just not going to have like an exabyte size array. So it generally saves quite a lot of space. So like I said, these are fence posts. So if we're taking a look at our offsets here, this is the far right side. So if you're taking a look at your offsets more directly, if you might have like 5 here, there's 5 offsets. But what that really means is that you have 4 data records in your array. And what this format does is each of these offsets, it's like a sliding window of 2 as you go down, is the start and end of every data record in your data array, so that you know how long something is. You just grab that one record out. And this is partially a hedge against corrupted data. I did a lot of like fuzz testing and stuff on this format so that I know that the part that's interpreting it is correct. And this kind of came out of part of that. So 5 offsets would mean 4 records because of the way we're doing fence posts. Special case, 0-length array is just like 2 bytes long. We have 0 offsets. We know it's just a 0-length array. So let's take a look at an example here. The arrays themselves, as usual, type byte. We have our header section here, and then we have the data that comes after it here. So our array is in the top left here. We're looking at like just an array of true and false in JSON. And if we want to store that, we have an array here, and it has a header. Like we saw before, there's a number of offsets, which remember is fence posts, so the length is actually 2 here, but the number of offsets is 3. There's a length of each offset in bytes. And then we have our offsets there. And immediately after that is all the data. So this is the way it's laid out, like either on disk or wherever you're storing it. But remember, whenever we need to read these, we have to actually grab something out of it. We have to read it in order to interpret it. And the way this is set up, you only need to read like 3 bytes. And then you create a couple of slice headers, and then you're done, just to understand the way the array looks like. All you need is the number of offsets and the length of each one. And then we end up creating like a slice header that points to all these offsets, and a slice header that points to all this data. We don't need to copy it anywhere. So now we have basically our struct in memory. We can interpret the array as needed. So if we're looking at this example, there was 3 different types of queries that we had for an array, right? We had indexing, we had slicing, and we had iteration. So in this case, if we're looking at indexing for just getting the 0th element, we can grab the first offset and the second offset, and that tells us exactly where that data is in our data section. So in this case, it'd be like 0 and 2. And then we take those, and we go into the Go slice that points at that data and just slice that out. And we can go back and interpret that and deserialize and do whatever we need to with it. And all the while, we don't need to copy anything. All of this is a read-only type of query. So if you have your information in a place where you don't need to copy it, like if your database has some ability to just give you a pointer to the memory map file, for example, the only things you really need to copy out are like the first 3 bytes in this example, and everything else after that you just have to access as needed. So that's for indexing. And if you go to, if you want to talk about iteration, it's a sliding window of 2. So in this case, there's only 2 windows that you could do. It's 0 and 2, and then 2 and 4. But you can imagine if we have like 1,000 of these offsets, you just have 999 of these sliding windows. That allows you to go through, and for every single one of those, kind of go slice data out of the array and then apply a subquery on that slice. You go and interpret it recursively. You can apply whatever subquery you want on it. So for slicing, this is also pretty interesting. It's a constant time operation for this because we have this thing in memory. We have slices that point to your offsets. We have slice header that points to the offsets. We have slice header that points to the data. And what we really need to do is just kind of reduce our view. And what that effectively means is just slicing our offsets array. So just kind of cut off some of them, and then you suddenly can't see part of it anymore. So in this case, if we're looking just to slice it to index 1 only, if we want just record 2 in view, what we end up doing is just removing the ability to see the rest of that data. So we'll get rid of the first offset. We only have 1 window here. In our in-memory structure, we had to change the number of offsets just so we have that accounting done. But the data's still all there. Our view has just changed. So this ends up being a constant time operation. There's no copying done. And then we can go through and do whatever query we want after that, or deserialize it. Everything here, the way the code's written and the way the structure is set up, after slicing, it's symmetric to what it looked like beforehand. So you don't have to worry about any special cases of like a start or the end or anything like that, and that's where the fence posts come in. So we always have a start, we always have an end, and there's no special casing. Okay. Maps are a different beast. So maps don't have an ordering. We were just talking about fence posts in an array. So like the array can count on the next record being there, or at least some sort of end fence post, but with maps, they don't have that. They do have the same basic structure. We have like a header and we have data, but our header looks a little bit different. We have a number of records here, and that's 1-to-1 this time. There's no fence post, it's just 1-to-1. And then we have our offset length, like we saw before, the number of bytes each offset like takes up. And we have this new thing here called the length of the length. So that's the length in bytes of the length field in our header records, which we'll look at in just a second. This is all because we don't have an ordering. We can't rely on the next header record knowing where the end of our current record is. So, right, and then after that, there's just a bunch of header records that are all kind of packed in. So all these header records packed together, the size of which is proportional kind of to the number of records and the offset length and length. So we'll take a look at that in a second, but just to make this clear, in this case you'd have like 4 header records and then like 4 actual data pieces. So it's just 1-to-1 mapping. So what does each one of these look like? Well, they start with an intern ID, which I will explain in just a second. And then we have an offset into our data, just like we had in the array. And then we have a length of that data, so that we know exactly what part to slice out of our data array to go interpret later. And that allows us a start and the end. Intern ID, also fixed size, just 4 bytes. So every single header record here is exactly the same size. And in theory, like we could do like a varint for the length, but the reason not to, I will explain in just a minute. Who's familiar with like what string interning is in Java or anything like that? Does anybody know what that is? Okay, some of you do. Java and other languages will do what's called string interning, especially whenever they're doing compiling. They'll have one copy of the string, and then people get a pointer to that string. We're not doing pointers here, or references or anything like that, but what we're doing is we're creating a mapping from the keys in the map. All of those string keys, instead of storing them as strings, what we're going to do is we're going to assign them an intern ID. So there's an assumption here in this system that maps are going to have very repetitive keys across many different records. This is, if you think about it, maybe in terms of Netflix, like just say video history or something. We're going to have people who watched Orange is the New Black, like lots of them, and they're all going to have a map with like a key, Orange is the New Black, and if we store that string everywhere, it's going to get really huge. Instead, we're going to store 4 bytes. So whenever we ingest a map into the system, we're going to assign these intern IDs to all of the keys in this map and just store those instead of the strings. And separately, we'll store like the forward and reverse mappings for these keys. So for an example here, we might have the key true to 1 and false to 2. So when you look at the header records, I didn't say this before, but like how are we actually going to do these lookups whenever we want to do a point lookup? Well, we can take that string that you give us, go get the forward mapping to the intern ID, and then we go do a lookup. But the way the header records are laid out, they're actually sorted. So we sort the header records by intern ID, and then you can do a quick binary search on it instead of doing something silly like a linear search. So in this case, it's just an example, like you might have intern IDs 117, 52, 195. It doesn't really matter what they are, but they are in order. And again, empty map, special case, it's just like 2 bytes. The length is 0, so we're just done. Okay, this is an example. It's going to take a minute to talk through, but it has all the pieces that we just looked at. Above is the one that we're storing. So we have a string false to the value false, string true to value true. And we have everything that we had in the header. So the number of records that we have, 2. The length of each offset is just 1. We don't really need that much because it's less than 255 bytes long. And then the length of each length value is also short because no one record is that long. So again, these are the same length. And when you look at it, if you want to do a binary search on a giant array of these all kind of packed together, you need to know that they're all the same length so you can calculate where to jump to whenever you're going to go to the middle of the section that you've picked out. And that's not really possible if you do a varint, because it could be different sizes for different records, and then you're forced to do a linear search. So this allows you to do binary search. We had 3 different types of queries that we could do on maps. We can look up a key, and it's the same thing if you're doing multiple keys. We could get the keys, just the string keys out of the map, and then we could iterate over them and apply a subquery to all the values. So in this case, if you're looking at the map, oh right, I didn't explain the records. So these kind of bigger boxes, it'll just look really noisy if I made them 4 boxes. So just those are 4 bytes long. And you can see that 1 here, it corresponds to true, but that was the second one in the map. No ordering, right? It's only ordered by intern ID, and that's entirely random. Effectively, these end up going through a Go map, so we have no control over the ordering. So it's definitely random. If you insert the same map with 1,000 keys twice, you're going to end up with entirely different intern IDs in the representation. Well, in 2 separate servers. If we get it inserted twice, we end up with the same intern ID because we're storing it, right? So here, if we wanted to go look up the value for true, we do a quick binary search on the header records. Very simple in this case, there's only 2, so we'll end up with record 1, and we'll be able to go to our offset 0 and our length 2, slice that Boolean right out of the data array, and then go interpret it. The other thing that we wanted to do with this, getting the map keys. So we can, because we have these fixed size header records, what we can do to just get all the keys of the map is just kind of iterate all the way down all of these header records and do the reverse mapping from intern ID to string and insert all of those into a big array in memory, and then we have all of our map keys. So that's it's sort of like a special internal API only for those queries, but that's the way we'll be able to go through and get all the keys. Those are not going to be in order, again, because we're kind of running through a Go map on the process here in the actual system. And the last is for iterating over all the values and applying a subquery. So we have these header records. We can do the same kind of iteration where we just go boom, 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 all the way down. Except now, instead of just doing the reverse mapping, we're going to do the reverse mapping, and then take this start and end and go slice the data out and apply a subquery. We could take the result of that query, associate it with the key that we took out, and then we have the return value. And that query itself could be recursive, et cetera. That's kind of a composite. It's recursive, the way the queries work too, just like the data. Okay, performance numbers. This is what everybody gets excited about. But I should note, before we even get into this, these are performance numbers around the specific operations that you just saw, and they don't necessarily represent how fast a real system would be, because a real system has disk, it has memory bandwidth, it has a certain number of CPUs. It has to deal with a real-world system where you might be in Amazon and you have a noisy neighbor who decided it would be a great time to find the next Mersenne prime. So this is not necessarily the perfect representation of what a real-world system looks like. So everybody wants to know how fast it is. Obviously, it depends on a lot of things. If you want to ask for a 4 gigabyte string, it's going to take longer. 4 gigabytes just takes longer to write out of a network socket than 6 bytes does. How complex the query is. So remember, these queries are recursive. I didn't really show a great example for recursive queries on recursive data just because it gets really complex on a slide. But you can imagine if you have 6 levels deep of maps, you could be iterating 3 different times and then getting different keys out of different places. And so it's a lot more work if you have a lot more complex queries. how many CPUs you have at your available, the load on the system, and then the speed of the underlying data storage. If you're storing this on a tape drive, it's going to take longer. All those caveats aside, let's just take a look at some numbers. This is fun for me. So serializing, these are all the scalars. Don't go scribbling down all the numbers. I'm going to post these slides on SlideShare right after this. I'm going to tweet it out. My Twitter's handled right at the end, so you'll get it. Just relax. What I find interesting about this in particular, the Booleans and then the ints and floats, they're not that much slower. Now these benchmarks were done, I should mention that these are like 30 times, like do the benchmarks 30 times, and then I use benchstat to generate these numbers. So it's not just like one run. I did them all on this laptop. I don't remember the model, or I don't know the exact CPU. It's an Intel 64-bit x86. So for integers, it's not that much slower than a Boolean. And this is because Intel is amazingly good at doing superscalar execution when you have like shift and OR and shift and OR and shift and OR, and they do this extremely fast. So also the string is just 6 bytes long. It's going to go up as you have longer strings. I don't have any other numbers for longer strings, but it's just going to go up. What I find also very interesting is that deserializing is much faster. I don't know exactly why this is, to be honest. I think it's because on Intels, whenever you grab like the 8 bytes as little endian, it's already little endian, so they just kind of need to like change the way you're looking at it, like conceptually, and it doesn't really need to shift any bytes around. But yeah, it's actually faster to deserialize, which is great. Lots of numbers, a couple things to focus on. So we have 0 and then 1 to 1,000,000 through orders of magnitude, so like there's 6 orders of magnitude there. And then same thing for maps. Oh, I should mention, integers. Keep in mind this number, 26.6 nanoseconds, okay? That's kind of an important number because all of these different benchmarks here are done with arrays of integers and maps of like a string representation of the integer to the integers. So the way these have to work is like I have to serialize something in the array. I don't have any dummy values, so all of these are like 26.6 times like 1,000,000 is how long it took to just serialize the values, and then you got to subtract that. I didn't do the math here, but you can if you want to later. A couple things to notice here is really fun actually for me to look at this. It's very linear for arrays. I translated the output of benchstat into like nanoseconds only so that you can kind of see how it goes up. There's some fixed overhead, but it's pretty much linear for arrays. And then for maps, there's some fixed overhead, and then it goes kind of linear, and then suddenly it goes n log n. This is really fun to look at because it's a very real-world example of how like big O notation works. When you're in like the less than 10,000 range, it's pretty much linear. But because we're sorting those header arrays, we end up with this big O of n log n, which means after maybe 100,000 elements, you're really starting to feel that sorting as being your bottleneck. I'm not like saying that's a bad thing. I just think it's fun to look at numbers showing you a real-world example of how that works. So deserializing, again, is slightly faster. Arrays, again, are linear. And maps, this is cool to me to look at. What we're doing is we're taking all these values and we're shoving them into a Go map. So if you have maps of maybe like less than 100,000 elements or so, it's fine. Everything's kind of good. N is small, right? But once you get up to 1,000,000, it's suddenly got like 2x slower than you might expect based on the previous trend. So I don't know why this is, but I think it's because the way Go maps work, whenever they get really big, they end up slowing down. Be cool to investigate. I don't know why exactly that's working that way. Okay, I'm sorry I'm throwing these like lots of number slides at you. This kind of works out. You don't need to look at each individual number. Something to notice though, if we go back, ints are 26.6 nanoseconds, right? So deserialize. If we go to an array, like getting one element out of an array, remember these are integers, it takes roughly 26 point something nanoseconds, basically no overhead whatsoever to go get something out of an array, as long as you have the thing in memory somewhere, which is really cool. I mean, you would kind of expect that you're just kind of calculating that offset, and then again, getting the offset into the data array. Slicing, again, is a constant time operation. So when you're looking at this, you're just kind of doing a go slice operation, and you're subtracting one integer. And that's all it takes, is just like 70 some odd nanoseconds to do it. And map gets this, again, real world example of big O notation. This is really cool to me. When you're looking at this, it's binary search, so it's log n, right? And you're looking at what, 1, 2, 3, 4, 5, 6 orders of magnitude increase from 1 to 1,000,000. And the latency that it takes, the time that it takes to do that lookup is only 1 order of magnitude difference. This is a pretty straightforward, this is log n at work. It's just, I don't know, for me sometimes it's just exciting to see oh wow, those people who were teaching me in college, they actually knew what they were talking about. And map keys, I don't really have an explanation for why it's going slower and slower, somewhat super linear as it gets bigger. I don't know, but it is getting slower and slower, slightly. But basically, you're allocating a whole ton of strings and a giant array of strings, so it's just going to take some time. Okay, so future. Remember way back when we were talking about integers, 8-byte integers and 8-byte floats, why I wanted to keep them as 8 bytes instead of doing varint? Well, what if we wanted to be able to replace those in place? Well, now if I have 8 bytes reserved all the time, I know that I can just take any other int or any other float and stick it in there, and don't have to shift any data around. There's nothing to mess with. You just go put it in wherever it's stored. I also want to be able in the future be able to append to arrays and add new keys to a map. These are going to necessitate changes to the format that you just saw. So now that we've got all this worked out, we're going to have to go mess with it again. And there's other operations that you could do, like increment or decrement or what have you. And maybe we could figure out a way to do compression, but the way it's set up, it kind of jumps around a lot. So it may be hard. I don't know. I'll find out. Okay. I know there's a lot of information I just threw at you. So if you have any questions, I'll be happy to take them. You can see my Twitter handle. You can email me. You should go check out the tech blog at Netflix. We write about a lot of cool things. My team has done a few blogs on there before on EVCache, which is the other product that I work on. And with that, I'll take any questions that you all have.